So we are going to look at the tangent function today, see what the graph looks like, and then do some transformations of it. There's some fairly big differences between the sinusoidal functions we have been looking at and the tangent function. The biggest is that it's not a sinusoidal function. Okay, it does have a period, it does repeat itself, but it's not that wave shape that we're used to working with sine and cos. So we'll sketch the graph of tan, we'll look at the amplitude, domain, range, period. We're going to see that there's asymptotes for the graphs of the tan function, and we'll talk about where those x-intercepts are, and also look at solving problems by analyzing the graph of tangent function. So we want to graph tan theta between negative 2 pi and positive 2 pi. We'll talk about its characteristics. And so we'll do this by setting up a table of values here. And then we can use our calculator. In this case, all of these angles are in radians, so we need to be in radian mode to do this. So if you take the tangent of 0 on the calculator, you get 0. If you take the tangent of pi on 6, and incidentally, you also could, if you wanted to, use the unit circle to get these values. The only difference is that on the unit circle, all the values are exact values. To graph them, it might be better to have them as decimals. So at pi on 6, it's 0.6. At pi on 4, you might remember the tangent is 1 because sine and cos are the same value. The tangent of pi on 3 is 1.73. The tangent of pi on 2, you get an error. It doesn't exist. It's infinite. And that's where the first vertical asymptote will be. The vertical asymptotes will occur where the tangent doesn't exist, where it's undefined. Okay, and we can continue on using our calculator to get these values, but I'll just fill them in from here. At 2 pi on 3, it's negative 1.73. At 3 pi on 4, it's negative 1. 5 pi on 6, it's negative 0.6. At pi, it's 0. At 7 pi on 6, it's 0.6. At 5 pi on 4, it's positive 1, 1.73. At 3 pi on 2, again, it doesn't exist. That's where our next vertical asymptote will be. And here's the remaining values. So we can plot these on a graph. We have the point 0, 0. At pi on 6, which is the scale of this graph, between 0 and pi, it's divided into 1, 2, 3, 4, 5, 6 equal sections. So each section is 1/6 of pi, or pi on 6. So at pi on 6, we're at 0.58, just above 0.5. At pi on 4, or a quarter pi, which will be 1.5 units, here we're at positive 1. At pi on 3, which is 2 pi on 6, we're at 1.73. And then at pi on 2, or 3 pi on 6s, we have our first vertical asymptote. And we have our next vertical asymptote at 3 pi on 2, or 1.5 pi's. Okay, we can go back now and finish plotting our points. At 2 pi on 3, which is 4 pi on 6s, we're at negative 1.73. At 3 pi on 4, we're at -1. At 5 pi on 6, we're at -0.6. At pi, we're at 0. At 7 pi on 6, we're at 0.6. At 5 pi on 4, we're at 1. At 4 pi on 3, we're at 1.73. That's 8 pi on 6s. Okay, that's 1.73. And then again at 3 pi on 2, we have our next vertical asymptote. At 5 pi on 3, we'll be at -1.73. At 7 pi on 4, we're at -1. At 11 pi on 6, we're at -0.6. And at 2 pi, we're back to 0. So if we first graph between the two asymptotes, between pi on 2 and 3 pi on 2, this is what the graph looks like. Looks something like that. There's actually a point of inflection at pi, the point pi comma 0. Point of inflection is where the graph changes its concavity. So what we see happening here is at the start between 0 and pi on 2, we basically have 1/2 of a cycle. One full cycle is between the asymptotes, and the asymptotes occur every pi radians. The first one is at pi on 2, the next one is at 3 pi on 2. That's 2 pi on 2 away. 2 pi on 2 is pi radians. So there will actually be a vertical asymptote at -pi on 2 and -3 pi on 2. And the pattern for the graphs will stay the same. So between -2 pi and +2 pi, this is what the graph will look like. The distance between the asymptotes is pi radians, and that also shows one cycle of the graph. So if we start talking about the characteristics of this graph, the first thing we would say is there is no amplitude, because the amplitude is the distance from the horizontal midline to the maximum or down to the minimum. This graph has no max or min. The closer it gets to the asymptote, it's just going to keep going either upwards or downwards forever, depending on which side of the asymptote we're at. On the left side of pi on 2, the graph is going upwards forever. It's approaching positive infinity. On the right side of pi on 2, the graph is going downwards forever. It's approaching negative infinity. So there is no amplitude because the graph just continues on forever, rising and falling. Okay? The period of the graph is pi radians, or 180 degrees. So that's another significant difference between this graph and the graph of sinusoidal functions. For sine and cos, our period for the base graph is 2 pi radians, or 360. For tangent, it's different. It's half of that. It's pi radians, or 180 degrees. Okay? The domain of this is also different. For sine and cos, the domain was all real numbers. But here we have the restrictions. We have our vertical asymptotes. The first one being at pi on 2, and then all the other ones are pi n radians from pi on 2. So the domain for this is all values of x such that x cannot equal pi on 2 plus n pi, where n is an element of integers. Can't really state the domain using interval notation. You have no choice but to use set notation for this. Our range, that'll be different as well, because this range goes from negative infinity to positive infinity. And that never changes. I said earlier too that we'll often be asked to find or state our x-intercepts. The first x-intercept is at 0. The next one, because the period is pi, the next one will be pi radians away, and then another pi. From 0 we can go to negative pi, negative 2 pi. Our x-intercepts are at every multiple of pi, including 0 pi. N is an element of integers, 0 is an integer. So there's the x-intercepts. They go on for infinity following that same pattern. So it doesn't matter whether your x-axis scale is in degrees or radians, it's done the same. Instead of having asymptotes at every pi on 2 radians, now they'll be at 90 degrees and then every 180 degrees from there. You're still going to have your first x-intercept at 0, and they will be every 180 degrees. So the graph will look the same. This is just going to be a sketch. So whether you're in degrees or radians, the graph will look the same. And when we talk about the characteristics again, we would say there's no amplitude. The period now would be in terms of degrees instead of radians. We can say that our x-intercepts are now every multiple of 180 degrees. Our domain, again, we need to use set notation for this because we have asymptotes starting at 90 degrees, so x cannot equal 90 degrees plus every multiple of the period, every multiple of 180 degrees. Where n is an element of integers. Our range, again, will go from negative infinity to positive infinity. The scale on the y-axis doesn't change. So there's our characteristics. So now what about if we do some transformations on the graph of tan x, for example, tan 2x. So in this case, we have a b value of positive 2, which remember causes a horizontal stretch about the y-axis by a factor of a half. Remember the horizontal stretch factor compared to the b value, they are reciprocals of each other. So that's going to change the period. Our period will now be half of what it was before. Instead of being 180 degrees, and I'm using degrees in this case because that's the scale on the x-axis, now our period will be every 90 degrees. So remember the graph of tangent starts at 0, 0. The next one will be now 90 degrees away because that's the period. Every 90 degrees will be at another x-intercept. So at 180, at 270, and at 360, we're going to have an x-intercept. Also, normally our asymptotes, remember they were at 90 degrees plus every multiple of 180 degrees, but now those will also be half of what they were before because we're horizontally stretching by a factor of a half. So now they will be at 45 degrees plus 90 n degrees, where n is an element of integers. So our first asymptote will be at 45 degrees, which is halfway between 30 and 60. Another 90 degrees will be at 125. Sorry, 135. Halfway between 120 and 150. And again, once we get our first asymptote, or every multiple of 90 degrees, they are halfway in between the x-intercepts. Halfway in between. And really, this is all we need to sketch our graph. So the other characteristics that we can talk about, okay, we've already stated our periods and where our asymptotes are. So our domain all values of x such that our first asymptote again is at 45 degrees. So x cannot equal 45 degrees plus 90 n degrees because now our period is 90 degrees. Our range hasn't changed. It never will, even if the graph is shifted up or down. But our x-intercepts have also changed. Our first one is at 0 degrees, but now they are every 90 degrees, because again, that's the period. Okay, so there's that graph. So for this next one, we want to sketch the graph of y equals tan of x minus 30 degrees plus 1 on the grid below. So in this case here, we're going to have a phase shift of 30 degrees to the right. And we're going to have a vertical displacement of 1 unit up. So the graph of tangent normally starts at 0, 0. This one will shift 30 degrees to the right and 1 unit up. So that first point of inflection will be at 30, 1. Our period hasn't changed. Right? Our period hasn't changed because there's no b value, no horizontal stretching. So our period is still every 180 degrees. So from 30, if we add 180, we'll be at 210. That'll be the next point of inflection. And then another 180 from there will be at 390, so just past 360. There. Our first asymptote was at 90 degrees, but it also goes to the right 30 degrees, so it'll be at 120. And then 180 from there will be at 300 degrees. Really, this is all we need to sketch our graph. Our point of inflections are there. Well, that one's not very good. Do a better job of that. So the graph would look something like that. So the domain of this, that will change. We would say x cannot equal, let's do this right, using set notation. So our first asymptote was at 120 degrees, and our period is still 180. There's our domain. Our range hasn't changed. Still goes from negative infinity to positive infinity. Now our x-intercepts changed. And probably the best way to find your x-intercepts is by using the graphing calculator. In this case, we're going to graph in terms of degrees, so our mode must be in degrees. We're going to do y equals the tangent of x minus 30 plus 1. My windows have to be in terms of degrees, so if we go from negative 30 up to, let's say, 300 or let's say 400 degrees, a scale of 90 degrees, I'll go from negative 10 to positive 10 on the y-axis and a scale of 2. So we're doing this so we can find out where our first x-intercept is. So if I go into trace, actually I'll find my first 0. Second function, trace, I want to find the first 0, which is number 2. I'll put my left boundary at, say, negative 20 degrees, and my right boundary at 50 degrees. So it's at negative 15 degrees. So my sketch is off a little bit, obviously, but the calculator is quite useful then to find out where that first x-intercept is. It's actually at negative 15 degrees. But the period is still 180. So every 180 degrees from negative 15, you're going to have x-intercepts. So there's your x-intercept. Okay. All right, so there's an assignment there that you can work on. I will post the solutions to Google Classroom so you can check your answers. Remember, Monday, we're going to start Chapter 6, and you're also going to write your Chapter 5 quiz. So that'll be happening on Monday. And then after chapter 6, that'll be the end of unit 2, and we'll have our next unit exam. All right?